having a great day today. So today I'm going to go through the Chapter 2, Part 2 test review in this video. This review is in your packet, but it's also online if you want to print out an extra copy. That's totally fine. You might not have enough space to do all your work on here, so you can grab an extra piece of paper if you need it. On part of our test, you will be allowed to use a graphing calculator. So on numbers 1 through 24, on the test review, that is what you are allowed to use a calculator on the actual test. So let's start with numbers 1 through 4. Our question says, determine the degree and end behaviors of each function. This comes from section 2.2a, where we first learned about degree and end behaviors. Question 1, they give you the function. To tell the degree, we're just going to look at the highest exponent that we see. The highest exponent is 3, so this is a degree 3 polynomial. And it is odd, because 3 is an odd number. To tell the end behaviors, you need to know the degree and the leading coefficient. That's what we abbreviated LC. The leading coefficient is the number that is directly in front of the highest exponent, which is -2 here. It is negative, so that's what I'm going to write down for the leading coefficient. It is negative. Since the degree is odd and negative, the graph is going to look like the negative odd function x to the third. And that's what negative x to the third looks like. Since our function is odd and negative, it's going to have the same end behaviors as that function that's odd and negative as well. Using our limit notation, let's go write the end behaviors. The limit as x goes to -infinity, which is to the left side, you can tell that the graph is going to go up to +infinity. Now let's do the right limit. As x goes to +infinity, the function, you can tell here, is going down to -infinity. So in question 1, that's all we needed to know. The degree was 3, and then using the degree and leading coefficient, we were able to state the end behavior. On question 2, we're doing the same thing. The degree is the highest exponent, which is 4. That's in even numbers. The degree is even, and it's 4. To tell the end behavior, we already stated the degree. The leading coefficient is positive, because that's a +4. Just by knowing the degree and the leading coefficient, we can think of another function that is even, like the squared function, and positive, that looks like this. Since our function is even and positive, and this function is even and positive, they're going to have the same end behaviors. So the limit, as x approaches -infinity of f of x, on the left side, the graph is going up to +infinity. And now let's do the right side. As x approaches +infinity, so as x goes to the right, the function is going up to +infinity as well. So that's all you needed on that question, the degree and the end behaviors. On question 3, to find the degree, you'll see that as we look at the function, it's already been factored for you. So to find the degree, I'm going to add all the exponents together. 1 plus 1 plus 3 makes 5. So this function is an odd degree because 5 is an odd number. The leading coefficient is in the front here. All of those leading coefficients are positive. So if I was to FOIL that factor through, I would find that the leading coefficient is also positive. An odd function that's positive is x to the third. It's a parent function we've studied, and it looks like that. Since my function is odd and positive, and this function is odd and positive, it's going to have the same end behaviors. So the limit as x goes to negative infinity, which is the left side, the graph is going down to negative infinity. And the right-hand limit, as x goes to positive infinity, the function is going up. That's all you need on that question, the limits and the degree. Now on question 4, this one's also been factored for you. So to find the degree, using our properties of exponents, I'm going to add all of the exponents together. 2 plus 1 plus 1 makes 4, which is an even number. So this is a degree 4 polynomial. To tell the end behavior, let's also look at the leading coefficient. The leading coefficient here is negative, because if I FOILed all of those factors through, the leading coefficient would be negative because of that negative in the front. Now let's compare it to something we do know. A function that is even and negative is like negative x squared. Since my function is even and negative, and this function's even and negative, they're going to have the same end behaviors. The limit as x approaches negative infinity of f of x is what the graph is doing on the left side, which is going down. So it's negative infinity. And on the right side, the limit as x approaches positive infinity of f of x. On the right side, the graph is going down to negative infinity as well. So that's a little review for you over how to state the end behaviors and degree of polynomials, if they're in factored form or if they're just polynomial functions. On questions 5 through 8, it says, find the zeros of the functions below and state the multiplicities. This comes from section 2.2a as well, where we learned about finding zeros and stating multiplicities of those zeros. So to find the zeros, I'm going to set the entire equation equal to 0. Then we're going to look at the right side and see if we can factor it. This right side is a trinomial. There's no GCF, because this is A, B, and C, and none of those are divisible by any common factor except for 1. So now we're going to factor it. There are 3 terms, so I'm going to use that X method we learned in class. A times C, 5 times 6 is 30, and negative 17 goes in the bottom part of the X. Now 2 factors that multiply to make 30, but add or subtract to be negative 17, are negative 15 and negative 2. And you can sit there and think about what factors would work, but those are the only factors that will work, negative 15 and negative 2. So now I'm going to rewrite this polynomial. In place of negative 17x, I'm going to use the 2 factors, negative 15x and negative 2x, and bring that plus 6 on down. Now you'll notice we have 4 terms on the right side, which means we're going to use grouping to factor the right side. So group and group. The GCF of the first 2 terms is 5x. When I factor out a 5 and an x out of both terms, that leaves us with x minus 3 on the inside. The GCF of the last 2 terms is negative 2. When I factor out a negative 2 out of these 2 terms, that leaves us with x minus 3. Now we're going to pull out the GCF here, which is x minus 3, and group the outside pieces together, 5x minus 2. Now that the right side has been fully factored, because we use the X method in grouping, I'm going to split these factors apart and set them equal to 0 to find the zeros of this function. Add 3 to both sides so that x equals 3. I'm going to write that up here. There's one solution for x. Now to find the other value of x, I'm going to solve this equation. First, move the constant over by adding 2 to both sides, so that 5x equals 2, and then divide both sides by 5. So x equals 2 over 5 is the other value for x. And those are the two solutions to that polynomial on question 5. Since each of these factors had an exponent of 1, they only occurred once, so I'm only writing each of those one time. On question 6, we're going to do the same thing, set the entire function equal to 0. And use a factoring strategy to factor the right side. This does have 4 terms and no GCF, so I'm going to use grouping to factor the right side. The GCF out of the first 2 terms is x squared. When I pull out an x squared out of the first term, we're left with x, and out of the second term is just 2. The GCF out of the second 2 terms here is negative 25. When I divide that out of both terms, I'm left with x plus 2. Now you'll see that the GCF here is x squared minus 25 comes out, and x plus 2 was the GCF that they had in common. I'm going to keep factoring because this x squared minus 25, that's a difference of perfect squares. So we can factor that into x minus 5 and x plus 5. And keep your x plus 2 there. Now that the right side is fully factored, I'm going to split each of those factors apart and set them equal to 0. And solve. And the last one down here. Going back up to the top, to add 5 to both sides, x equals 5 is our first solution. This middle equation, I'm going to subtract 5 to both sides, so that x equals negative 5 is the other solution. And last one, subtract 2 to both sides, so x equals negative 2 is the last solution. So those are your 3 solutions to that polynomial. They each occurred only once, because that was the exponent on each factor. So I'm only going to write those once. On question 7, I'm going to set the entire function equal to 0, just like I've been doing, because that's how you solve for zeros. You'll notice that this one is already factored for you, so they've done the work for you. All we got to do is solve for x. And I'm going to split each factor apart and solve each one of those for x. Because it was already factored for you, you don't need to factor. We're just solving. On this first equation, I'm going to divide by negative 4 on both sides to get x cubed equals 0. To undo something that's cubed, we're going to take the cube root of both sides so that x equals 0. That's our first solution. Because this had an exponent of 3 with the x, that means that this has a multiplicity of 3. And I'm going to say that with M3 just to shorten it. So that's our first solution. Let's come over here and do the next one. First, take the square root of both sides to get rid of the squared, and then add 2. So x equals 2 is our second solution. This factor, though, had an exponent of 2, which means this has a multiplicity of 2. It occurred twice. And the last one here, I'm going to take the cube root of the left and the right side to undo the cubed. That leaves us with x plus 3. The cube root of 0 is just 0. To solve for x, I'm going to subtract 3 to both sides. So x equals -3 is the last solution. This factor, though, had an exponent of 3, which means that solution has a multiplicity of 3. And those are your 3 solutions for x, along with all of their multiplicities. On question 8, I'm going to do the same thing. Set the entire function equal to 0 and solve for x. This one has also already been factored for us. So I'm just going to split each factor apart and set each factor equal to 0 to solve for x. On the first one, I'm going to take the square root of both sides to undo that squared on the x. So that x is by itself on the left. The square root of 0 is just 0. There's your first solution. This factor had an exponent of 2, so the solution has a multiplicity of 2. On the middle factor, I'm going to subtract 1 to both sides to get x by itself, so that x equals -1. This factor, even though it does not have an exponent here, it is an exponent of 1, and that's its multiplicity. Since it's a multiplicity of 1, I'm not going to say that it's a multiplicity of 1. We're just going to assume it from the solution. On this last factor, we need to take the square root of both sides to undo the squared. The square root of 0 is 0. Now to solve this, I'm going to add the constant over. So that 2x equals 1, and then divide both sides by 2. So x equals 1 over 2 is our last solution. This factor had a multiplicity of 2 because the exponent was 2. So those are your solutions to that polynomial. On questions 9 through 10, our directions say draw arrows to match the equation with the graph. And I gave you a hint here to look at the graph's end behavior. This does come from section 2.2a as well. To tell a function's end behavior, we need to check the degree and the leading coefficient. On question 9, the degree, the highest exponent, is 4, which means that it is even, because 4 is an even number. And the leading coefficient in the front is negative. Another parent function that we know that's also even and negative is negative x squared. It looks like this. Since our function is even and negative, and this function's even and negative, both functions are going to have the same end behavior. This function goes down on the left side and down on the right side. As you look at the two graphs that are on your test review, this function is the one that goes down on the left and on the right. So question 9 goes with this graph. On question 10, we're going to do the same thing. State the degree first. The degree is the highest exponent, which is 5, and that is odd. The leading coefficient is positive. Another function we know that is odd and positive, we've studied before, is x to the third. That looks like this. Because my function is odd and positive, and this function is odd and positive, they're going to have the same end behavior, going down on the left and up on the right. You can tell this function goes down on the left, up on the right. That's what makes question 10 match that graph. So that's a little bit of review for you over section 2.2a, where we learned about zeros and multiplicities and stating the end behavior of functions. On questions 11 through 12, it says use long division to divide. And I am specifying which type of division I want you to use on these polynomials. This comes from section 2.3a, where we learned about polynomial long division. There is a nice acronym that we wrote down that helped us remember the steps for long division. Was first we divide, then we multiply, then we subtract, then we bring down, and then the cycle repeats all over again. Before we do this long division, note that on the inside of this polynomial, we are missing the x term. So when we write out our division problem, using the long division symbol, 2x cubed minus 7x squared, in place of x, I'm going to put plus 0x to hold the place of that x term. Okay, you must do that to hold its place. And then minus 65 goes at the end. This x minus 5, since that's what I'm dividing by, it goes on the outside of the division bar. Now we're just going to go through our steps. First, we divide the first two terms. 2x cubed divided by x to the first. First, we'll divide the numbers. 2 divided by 1 is 2. And x cubed divided by x to the first, we're going to subtract those exponents, which makes x squared. Now we're going to multiply 2x squared through this binomial. 2x squared times x is 2x cubed. 2x squared times negative 5 is negative 10x squared. Next step is to subtract. Subtract the first term, and subtracting the last term just changes this to be a positive 10, right? Because two negatives will make that a positive. 2x cubed minus 2x cubed cancels out because it makes 0. Negative 7x squared plus 10x squared is 3x squared. Now I bring down and start the process all over again. 3x squared divided by x is positive 3x, because x squared divided by x to the first, 2 minus 1, leaves us with 1 there for the exponent. Now we're going to multiply. 3x times 1x is 3x squared. So I added those exponents. 1 and 1 makes 2. 3x times negative 5 is negative 15x. Subtract by flipping both of those signs. 3x squared minus 3x squared is 0. 0x plus 15x is 15x. And bring down that minus 65. We're almost done. Now do the same thing. 15x divided by 1x is positive 15. The exponents on the x are 1 minus 1, which makes 0, and that goes away, so we don't need an x with the 15 up here. Now I'm going to multiply. 15 times x is 15x. 15 times negative 5 is negative 75. And you can use a calculator there if you need to. Next step is to subtract by flipping both of those signs. 15x minus 15x is 0. Negative 65 plus 75 is positive 10. Since there's nothing else to bring down, 10 is the remainder. So let's go write out our final answer here. 2x squared plus 3x plus 15 plus positive 10 over what we divided by, x minus 5. And that is how you divide polynomials. On question 12, I'm going to do the same thing. We're not missing any terms inside of this first polynomial. So I'm just going to write it out as it's written. 4x cubed plus 20x squared plus 9x minus 28 divided by x plus 4. First, we're going to divide the front two values. 4 divided by 1 is 4. X cubed divided by x to the first, subtracting those exponents. 3 minus 1 makes 2. Now we're going to multiply. 4x squared times x is 4x cubed. 4x squared times 4 is 16x squared. Now we're going to subtract both values by flipping their signs. 4x cubed minus 4x cubed goes away because it's 0. 20x squared minus 16x squared is 4x squared. Bring down the 9x and repeat the process. 4x squared divided by 1x. 4 divided by 1 is positive 4. X squared divided by x to the first is just x. Now we're going to multiply. 4x times x is 4x squared. 4x times 4 is positive 16x. Subtract by flipping both of those signs. 4 minus 4 is 0. 9x minus 16x is negative 7x. Bring down the negative 28 and start all over again. We're almost done. Negative 7x divided by 1x is negative 7. Negative 7 times 1x is negative 7x. And negative 1 times 4 is negative 28. Flip both of those signs for subtraction. And you'll notice both of those values cancel out this time because they make 0. So there is no remainder when you divide those two polynomials. So our answer is just 4x squared plus 4x minus 7. That's a little bit of a review over long division with polynomials. On questions 13 through 14, it states use synthetic division to divide the polynomials. This comes from section 2.3b, where we learned about synthetic division. Before you divide polynomials, let's check to make sure we don't have any missing terms. We've got the fourth power and then the second power, which means we are missing the x to the third term. It goes from 4 to 2, so we're missing x cubed, which means we're going to put a 0 when we divide to hold its place. When you're using synthetic division, the first step is to solve what you're dividing by for x. I'm going to do that by subtracting 2 to both sides. So x is negative 2. That's what I'm going to use for synthetic division. When you write synthetic division, the coefficients go out in the front. Then negative 3, negative 8, and positive 4. Bring down the first term. Multiply negative 2 and negative 5 to make positive 10. And that goes in the next column. Now I'm going to add those together. 0 and 10 makes 10. Then multiply. Negative 2 times 10 is negative 20. That goes in the next column. Combine those together. Multiply negative 2 and negative 23 to make positive 46. Combine those together. Negative 8 plus 46 is positive 38. Then multiply. Negative 2 times 38 is negative 76. 4 minus 76 is negative 72. These are the coefficients in our new polynomial, and the degree just drops down by 1. So instead of x to the fourth, this first term is x to the third. The next term is 10x squared minus 23x to the first plus 38, because that's a positive 38. And this minus 72 at the end is the remainder. So minus 72 over what we divided by, x plus 2 goes at the end. That's how you divide polynomials using synthetic division. On question 14, we're doing the same thing. We're going to divide using synthetic division. You'll notice that we are not missing any terms this time. So let's go ahead and divide. First, whatever you're dividing by, we're going to set equal to 0. Add 6. So x equals 6. Now I'm going to come over here and use that for synthetic division. The coefficients are 4, 15, and 1. Bring down the first term. Multiply 6 and 4, and that goes in the next column. 15 plus 24 is 39. Multiply 6 and 39. You can do this in the calculator. It's 234. Add those together is 235. These are the coefficients of the new polynomial. And the degree just drops down by 1. So instead of x squared, this is x to the first plus 39 plus this last term is the remainder, 235 over x minus 6. So that's a little bit of review for you over dividing polynomials using synthetic division. Synthetic division and polynomial long division, they are different processes, but they get you the same answer. They're just two different ways to divide polynomials. On questions 15 through 16, our directions say use synthetic division to evaluate the polynomial for the given value. This comes from section 2.3b, where we learned about synthetic division. This also applies what we learned as the remainder theorem. And we learned about in section 2.3b that the remainder theorem tells us to just check the remainder to evaluate f of a number. So that's what I'm going to do. I'm going to use synthetic division, like the directions say, to check the remainder, and that's going to allow me to evaluate a number. Our number here is 3 that I'm going to use with synthetic division. The coefficients are 3, -1, +1, and -5. Bring down the first term, multiply, and add. Multiply 3 and 8, and add those together. Multiply 3 and 25, and add those together. The remainder here is 70. So by applying the remainder theorem that we learned about, f of 3 equals 70. On question 16, we're going to do the same thing. Use synthetic division and check the remainder to evaluate h of -1. It's -1, goes inside of the synthetic division box. 4 is the first coefficient. We are missing the x cubed term, and we're actually missing the x term here as well. So I'm going to put 0 in to hold x cubed, and 0 in to hold x, and then 5 at the end. Bring down the first term. -1 times 4 is -4. Combine those together. -1 times -4 is +4. Combine those together. -1 times 2 is -2. Combine those together. -1 times -2 is +2, and combine those together. The remainder here is +7. So by the remainder theorem, h of -1 is +7. So that's a little bit of review for you over the remainder theorem and how we can use it to evaluate polynomials. On questions 17 through 18, it says use synthetic division to determine if the given binomial is a factor. This also comes from section 2.3b. In that section, we learned about synthetic division, but we also learned about something called the factor theorem. And all the factor theorem basically says is that if the remainder is 0, then x minus a is a factor of f of x. So we're going to use synthetic division and once again check to see if the remainder is 0 to determine if the factor is a factor of the polynomial. To use synthetic division here, first going to need to solve for x by adding 4 to both sides. So x equals 4 goes in the synthetic division box. The first coefficient here is 1, but we are missing the x squared term and the x to the first term here. So I put zeros there to hold the place of x squared and x. And then 64 at the end. Now let's divide to check our remainder. Bring down the 1. 4 times 1 is 4 and add those together. 4 times 4 is 16 and add those together. 4 times 16 is 64 and add those together to make 128. Since this remainder is not 0, x minus 4 is not a factor. I'll move that up so you guys can see that a little bit better. Since this remainder was not 0, x minus 4 is not a factor of that polynomial. Let's do number 18. The same thing, we're checking to see if x plus 4 is a factor of that polynomial. First, we're going to solve for x by subtracting 4 to both sides, so that x equals -4. Now let's see what the remainder is when we divide by that polynomial. 1 is the first coefficient, 4 is next, 9, then 36. Bring down the 1, multiply, add those together. -4 times 0 is 0. Add those to make 9. -4 times 9 is -36. Add those together to make 0. The remainder here is 0. So since 0 is the remainder, x plus 4 divides perfectly into the polynomial. That means it is a factor of r of x. That was the name of the polynomial that we divided with. So that's a little bit of review for you over section 2.3b, where we learned about synthetic division, how to apply the remainder theorem like we did up above, and how we applied the factor theorem to see if a polynomial was a factor of another polynomial. On questions 19 through 22, our directions state find all of the real and imaginary zeros for the given functions. This comes from section 2.4. where we studied the fundamental theorem of algebra. And I'm abbreviating that FTA, so that's a lot to write out. Basically, what the fundamental theorem of algebra says is that the degree of a polynomial equals the number of zeros that the polynomial has. So let's go ahead and do 19 first. To find the zeros, kind of like we did at the start of the test review, I'm going to set the function equal to 0. Now you'll notice that the right side is x squared plus 49. Since we can't factor it, we're just going to solve for x by moving 49 to the other side. Negative 49 is on the left, and x squared is on the right. To undo something that's squared, I'm going to take the square root of both sides. The square root of 49 is 7. But because this is a negative, I'm going to use an I after the 7 because that's an imaginary number, right? I, we learned, is the square root of negative 1. That's why I have an I there next to the 7. I also took a square root, which means we need plus and minus there. X squared, when you take the square root of that, it's just x. So those are your two zeros. By the fundamental theorem of algebra, since this exponent is 2, our polynomial has 2 zeros. So that one is done being solved. On question 20, again, I'm going to solve by setting the entire function equal to 0. And then see if we can factor the right side. This has 4 terms with no GCF. So we're going to use grouping, because it's got 4 terms, right? We use grouping when you have 4 terms. The GCF out of the first 2 terms is x squared, which leaves us with x plus 3. The GCF out of the last 2 terms is 4, because both terms are divisible by 4. 4x divided by 4 is x. 12 divided by 4 is 3. The GCF out of those 2 terms is x plus 3. And x squared plus 4 is what we're left with. Now that I'm done factoring this, we can't factor the right side anymore. I'm going to split those factors apart and solve for x. First, subtract 3 to both sides, so that way x equals negative 3 is your first solution. Over on the right side, I'm going to subtract 4 to both sides. To undo something that's squared, you can take the square root of both sides. The square root of 4 is 2. The negative here makes it have an I with it, so it is an imaginary root. And since I took the square root, plus and minus are needed in front of the 2i. Those are your roots to that polynomial. The polynomial has a degree of 3, which is why we have 2 zeros here, the plus and minus, and 1 0 here. That way you have 3 zeros in all. On question 21, I'm going to start off by solving for 0 by setting the entire function equal to 0 and solving now for x. You'll notice that this is a trinomial, so let's see if we can use the x method to solve. 1 times 5 is 5, and then b is 4. Can you think of 2 numbers that multiply to make 5, but add or subtract to be 4? Let's think of some examples, like 1 times 5 makes 5, but 1 plus 5 does not equal 4. Another way you can make positive 5 is if we multiply negative 1 times negative 5. That makes positive 5, but negative 1 minus 5 does not make 4. So there's no way we can factor this polynomial. But we could solve using the quadratic formula, because it is a polynomial that we can't factor, we can still solve it just using the quadratic formula. This was the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. That's the quadratic formula. You will need to know that for the test. Make sure that you memorize this formula for your test. Now let's just plug in our values. B is right here, so negative 4 goes first, plus or minus. B is positive 4, because right there, squared, minus 4. In place of A is 1, and in place of C is 5. All divided by 2 times A, which we've already said is 1. So in that step, I was just plugging in the values A, B, and C. Now let's simplify. You do get a calculator on this, so feel free to use one if you need one. 4 squared is 16. 4 times 1 times 5 is 20. And there's a minus sign separating those two. 2 times 1 is 2 in the denominator. Now I'm going to come over here and simplify that. Negative 4 plus or minus the square root. 16 minus 20 is negative 4 over 2 still. Now let's keep simplifying this. Negative 4 plus or minus the square root of negative 4. The square root of 4 is 2. Because it's negative though, it's 2i because of that negative. That's what makes it imaginary. Then divided by 2. The last step here, you'll notice that 4, 2, and 2 are all even, which means you can divide all of those numbers by 2. Negative 4 divided by 2 is negative 2, plus or minus. 2 divided by 2 is 1i, and 2 divided by 2 makes this 1. Since dividing by 1 doesn't change the value, we're just going to leave the top, negative 2 plus or minus 1i. That's how you use the quadratic formula to find the zeros or to find the solution to a polynomial. This does check out because the exponent is 2. This does have 2 zeros with a plus or minus sign. On question 22, it states n of x equals negative 3x cubed plus 6x squared minus 12x. First, we're going to set the entire function equal to 0, because that's what we're solving for, are the zeros. Now I'm going to see if I can factor the right side. Since this is a polynomial, let's check the GCF first. The GCF over here, all 3 terms are divisible by negative 3, and they also have an x in common. So negative 3x is our GCF. Negative 3x cubed divided by negative 3x is positive 1x squared. 6x squared divided by negative 3x is negative 2x. Negative 12x divided by negative 3x is positive 4. Now that I factored, I'm going to split each of the factors apart and set them equal to 0. So 0 equals negative 3x comes from the first factor, and 0 equals x squared minus 2x plus 4 comes from the second factor. Solving the first equation here for x, I'm going to divide both sides by negative 3. To move that negative 3 to the other side, 0 divided by negative 3 is 0. So there's our first solution, x equals 0. Over here on the right side, x squared minus 2x plus 4, those don't have a GCF. If you try and use the x method here to come up with 2 factors that would multiply to make 4 and add and subtract to make negative 2, you're not going to be able to find anything. So the x method's just not going to work there. Instead of using the x method, we're going to use the quadratic formula. Just like we did on the last problem. First, I'm going to label A, B, and C. Now I'm just going to plug those values into the quadratic formula. Negative b, which is negative 2, plus or minus the square root, b squared is negative 2 squared, minus 4 times a times c, all over 2 times a, which is 1. Now let's simplify. This double negative makes that a positive 2 in the front, plus or minus. Now let's simplify the square root. Negative 2 squared is positive 4. 4 times 1 times 4 is 16, and I have a minus sign still in the middle, over 2 in the denominator. Let's keep simplifying the inside. 2 plus or minus 4 minus 16 is negative 12 over 2. Now we're going to keep simplifying. X equals 2 plus or minus the square root of negative 12. Let's come up here and simplify that out. To break down 12, I'm going to break it down using the prime factorization we talked about in class. Two factors that multiply to make 12 are 6 and 2. 2 is prime, so I'm not going to break that one down, but 6 we can break down into 3 and 2. Since there are two 2's here, 2 comes out. 3 does not have a pair, so it stays inside. And the square root of the negative here makes this have an I with it. So that's what the square root of negative 12 simplifies down to be. 2i root 3 all over 2 in the denominator. 2, this 2 and this 2 are all divisible by 2. So once again, I'm going to divide them all by 2. 2 divided by 2 is 1, plus or minus 2i divided by 2 is just I, root 3, and 2 divided by 2 makes 1 in the bottom. So that is our solution to that polynomial. That was a lot of work. You have one very similar to that on your test. On questions 23 through 24, it states write a polynomial function multiplied out with the given zeros. This also comes from section 2.4. In that section, we learned that if x equals a, so x equals some number, is a 0 of a polynomial, then the opposite value, x minus a, is a factor of that polynomial. So let's do our first one. On 23, the zeros are 4 and 3. Since 4 is a 0, x minus 4 is a factor. Since 3 is a 0, x minus 3 is a factor of some polynomial. Now to write the polynomial, I'm going to FOIL those factors through because they're two binomials, we can FOIL them, right? X times x is x squared. X times negative 3 is negative 3x. Negative 4 times x is negative 4x. And negative 4 times negative 3 is positive 12. Now we can combine like terms. Negative 3x minus 4x is negative 7x. That is our polynomial, so I'm going to give it a name, f of x equals x squared minus 7x plus 12. On question 24, these are the zeros I give to you. Since 2 is a 0, x minus 2 is a factor. Since 6i, it's an imaginary 0, but it still works the same way. Since 6i is a 0, x minus 6i is a factor. And same thing with the last imaginary 0. Since negative 6i is a 0, x plus 6i is a factor. Now to simplify this, I'm just going to FOIL. We talked about in class, though, it's best to work with the imaginary part first. So I'm actually going to go ahead and FOIL the imaginaries through first. X times x is x squared. X times 6i is positive 6ix. Negative 6i times x is negative 6ix. And last, negative 6i times positive 6i, negative 6 times 6 is negative 36, and I times I is I squared. Now let's clean up that a little bit, because we've got some like terms. 6ix minus 6ix, that makes 0, so those i's and x's go away. I squared, we learned, is the same thing as negative 1. So I can substitute in negative 1 here for I squared, which makes positive 36, right? Negative 36 times negative 1 is positive 36. Now I've got two binomials to FOIL through on this last part. X times x is x cubed. X times 36 is 36x. Negative 2 times x squared is negative 2x squared. And last, negative 2 times 36 is negative 72. There are no more like terms to combine together, so that's our polynomial. F of x equals x cubed minus 2x squared plus 36x minus 72. Alrighty, on the last page of your test review, the very back side, this is the part of the test where you will not be allowed to use a calculator of any kind, because this is the graphing part of the test. This comes from section 2.2, A and B, where we learned about sketching polynomial functions. So on the last two questions, it says sketch the graph. We're going to find the degree, zeros, and multiplicities of those zeros, the y-intercept, and the end behaviors of the polynomial. On question 25, this has been factored for us. So to find the degree, I'm going to add the exponents 2 and 1 together, which makes 3, and that is odd. So this is a degree 3 polynomial, which is odd. To find the zeros, since this has been factored for us, I'm going to split those factors apart and set them equal to 0 and solve. To get the squared undone, I'm going to take the square root of both sides. So that x plus 1 equals 0, because the square root of 0 is 0. Subtract 1, so that x equals negative 1 is our first 0. This has an exponent of 2, which means its multiplicity is 2. On the second factor, I'm going to add 3 to both sides, so that x equals 3 is another 0 of this polynomial. It has an exponent of 1, which means it has a multiplicity of 1. Whenever we're sketching polynomials, we also talked about how the multiplicity tells you where the graph bounces or passes through the zeros, which are essentially the x-intercepts. Since the multiplicity on the negative 1 is even, the graph is going to bounce off of that x-intercept at negative 1. Since the multiplicity at 3 is odd, the graph is going to pass through the x-intercept at positive 3. So here it's going to bounce, and here it's going to pass. Now let's get the y-intercept. To find the y-intercept, we're going to plug in x equals 0. So everywhere we see an x in the function, I'm going to replace it with 0. And then solve. 0 plus 1 is 1. 0 minus 3 is negative 3. And that was because of PEMDAS. I simplified the inside of the parentheses first. 1 squared is 1 times negative 3 is negative 3. So there's your y-intercept. 0 was the x I plugged in, and negative 3 is what we got out for the y. Now let's state the end behaviors. To state the end behavior, we need to look at the degree and the leading coefficient, kind of like we did at the very beginning of the test review. The degree we already stated is odd, so it was 3, which is an odd number. The leading coefficient in the front here is positive. Another function we know that is odd and positive is x to the third, which looks like this. Since my function is odd and positive, and this function's odd and positive, they're going to have the same end behaviors. The limit as x approaches negative infinity of the function. As x goes to the left, the function goes down to negative infinity. And as x goes to positive infinity, on the right side, the graph goes up. So those are your end behaviors. So using a different color, I'm going to graph what this looks like. The degree we know was odd. The zeros were at negative 1 on the x-axis and at positive 3. Another ordered pair that we had was the y-intercept at 0, negative 3. The end behavior tells us what the graph is doing on the left and the right side. On the left side, the graph was going down. So on the left side, the leftmost point, the graph is going down. At this x-intercept of negative 1, the graph is going to bounce off of that point and come back down. So the next point, which is the y-intercept, which it then passes through because it's got to get to the next x-intercept up here at positive 3, where it's going to pass through that point because it had an odd multiplicity right up here. That's what gave us the bouncing and passing. And this also goes up because that's what the end behavior said. So that's what our graph is going to look like. On the last question of your test review, we're going to do the same thing. State the degree, zeros, y-intercept, and end behaviors before we sketch this function. The degree we can find by adding all the exponents together. 1 plus 2 plus 3 is 6. That's what makes this function even. The zeros we can find by splitting each factor apart and setting them equal to 0. And last one here, x plus 3 to the third equals 0. To solve for 0 on the first one, I'm going to get rid of this negative on the x by dividing both sides by negative 1, so that x equals 0. That's our first solution, x equals 0. This has a multiplicity of 1 because the exponent was 1. On the middle factor, we're going to take the square root of both sides to undo the squared. The square root of 0 is 0. Add 1 to solve for x, so that x equals 1 is another 0 of this function. It has a multiplicity of 2 because that's what the exponent on the factor was. And this last factor here, we need to undo the cube by taking the cube root of both sides and then subtract 3 to get x by itself. So negative 3 is also a 0 of this function with a multiplicity of 3 because that's what the exponent was on that factor. Now we've got the zeros, let's talk about where it bounces and passes. The odd multiplicities, like 1 and 3, is where the graph is going to pass through those x-intercepts. And the even multiplicity is where the graph is going to bounce. So it's going to bounce with the even and pass through the odd. To find the y-intercept, we're just going to plug in x equals to 0. So, negative 0 times 0 minus 1 squared times 0 plus 3 to the third. You'll notice here that since 0 is in the front, and I'm multiplying every other factor together, this just makes 0, right? 0 times anything is still 0. So that's our y-intercept, 0, 0. The last thing we need to get here is the end behaviors. We find those looking at the degree and the leading coefficient. The degree we already said is even, because 6 is an even number. And the leading coefficient in the front here is negative. Another function we know that is even and negative is negative x squared, which looks like that, like a parabola reflected over the x-axis. Since my function is even and negative, and that function's even and negative, it's going to have the same end behaviors. So let's go write those. The limit as x goes to negative infinity of f of x. On the left side, this graph is going down to negative infinity. And the limit as x goes to positive infinity of f of x. As the function goes to the right, the graph is also going down. So those are our end behaviors. Now using those pieces, let's sketch what this looks like. We had x-intercepts at 0, positive 1, and negative 3. There was a y-intercept also at 0, but I already put a dot there. The end behavior, the graph goes down. We said, like right here, goes down on the left side. At that point, negative 3, the graph passes through it and comes to the next dot, which is at 0. At 0, the graph had an odd multiplicity, which we stated that up here, which meant the graph was going to pass through that x-intercept and go to the next green dot, where it has a even multiplicity at 1, so it's going to bounce off of it and come right back down. And that matches what we said here about the right side of the graph going down. So that's a picture of what that graph is going to look like. Before I conclude this video, I did want to make a note. There will be one completing the square with factoring question on your next test. We're going to review how to do that in class, but if you want to go ahead and look at section 2.1b, your notes and your homework, that would be a great way to review for that question as well. Please email me though if you guys have any questions. The test review key is online as well, so feel free to take a look at that in my work if you need to. But just let me know if I can help you guys prepare for this test. Have a good rest of your day, Huskies.